Alright gang, I'm going to work on number 41. Now, this is a minutia detail, but it's really important, and if you don't do it, you're going to get screwed up and very frustrated, and we don't want that to happen, so let me make sure I'm really clear on this. So anytime you're looking for where the function is increasing and decreasing, you have to know if there's any domain restrictions, because they will fall on your number line, and the behavior of the derivative, whether positive or negative, can change around domain restrictions. So you got to be real careful with that. All right, so meaning this original function here, f of x, there's no graph at plus or minus 3. Those are vertical asymptotes. So this has a domain restriction. You cannot use positive or negative 3. And so any domain restrictions have to show up on the number line. Now what I did when I took calculus was that I would put like a big X, because there's no picture here, so I can't make any conclusions. Like this can't be a max or a min. There's no picture to be a max or a min. Nothing exists here, right? These are vertical asymptotes. So I would sort of like cross them out. You can't have a max or min at a domain restriction. Only at a critical number. All right, so then in terms of the critical number, that will occur when the derivative is equal to 0 or undefined. All right, now watch the caveat here. These will be mutually exclusive. So if I set the numerator equal to 0, I get a critical number of 0. If I set the denominator equal to 0, so where the derivative is undefined, I get plus or minus 3. But plus or minus 3 is already a domain restriction, so therefore it is not also a critical number. These numbers should be not overlapping in any way, okay? All right, so now we're going to get 0 here. So this is a critical number here, which means it has the potential to be a max or min. These are domain restrictions on the end. And again, the function can change from positive to negative of the derivative around a domain restriction and a critical number. All right, so this is the number line where I'm looking at what the derivative is doing with the behavior of the first derivative. All right, let's go, let's play. So we're gonna pick something over here like -4. Now let me note that this is always a really nice thing to do. If something is constantly positive or constantly negative, I would make note of that and not waste your time crunching that piece, because you already know what the result will be. All right, so what I'm saying is that, like, since this bottom part is squared, this is always going to be positive. It's not sometimes going to be negative. It's never going to be negative. So I'm not even going to plug x values in here, because I know that it's going to come out positive. Whereas the numerator, since you have the negative in front and this is x is linear, this is going to end up being positive or negative, right? If x is negative, overall it's positive. If x is positive, overall it's negative, right? So that kind of idea. All right, so I'm starting with a -4. And again, you don't need the exact value, so don't waste your brain doing that. I mean, you can if that's more comfortable to you, but you really just want to know whether it's positive or negative. All right, so if I plug in a -4 into the numerator, it's going to end up being negative because of the negative in front, right? So you have a negative in front, a negative you're plugging in, all over a positive. So a negative times a negative is positive, so it's a positive over a positive, which is overall positive. Which means the first derivative is positive, which means the function is going up. So make sure you're relating what the derivative is doing to function. All right, let's pick something in here like -2. So if I plug -2 into here, it's again a negative times a negative, one from the equation, another one from the x, all over a positive, because this is always positive. So this is a positive over a positive, which is positive. So the derivative continues to make the function go up. All right, now over here I'm going to pick like a 2. So there's a negative in front times a positive x value all over positive. So negative times a positive is negative over positive. So overall this is negative, which means the function's coming down. All right, something over here like a 4. Plug a 4 in here, so it's a negative from here, a positive from here, over a positive from here. A negative times a positive is negative over positive, then a negative, positive make a negative. So this part, the function itself, will be coming down because its derivative is negative. All right, so now let's talk about what we just found. So we found where the function is increasing or decreasing. So the derivative talks about the behavior of the original function. So f of x is, let's start with increasing. On the domain of negative infinity to negative 3, there is no graph at negative 3. Don't want to include that. Then it picks up again at negative, on the other side of negative 3, and it goes to 0. Okay, so that's where the function is increasing. Okay, let's do decreasing. Decreasing goes from 0 to 2. Okay, we have a vertical asymptote here, and then it picks up again. Oops, sorry, I said that wrong. Always give me a second if my brain screws up. To 3, you got to go all the way to the domain restriction. So to 3, and then it picks up on the other side of 3, and it goes to infinity. Okay, so your book gives critical numbers part A, increasing and decreasing is part B. All right, so this is where the function goes up and this is where the function goes down, and then we just have part C, which is the relative extrema. Okay, so now when we look at this, you can never have anything, you can't have a max or a min on a VA, so there's nothing here. You can only have a max and a min at a critical number. So to the left we go up. On the left side we go up. Hold on a second. On the left side we go up. On the right side we go down. Like this. So this is making a maximum. Now try to remember when you are figuring out where it is, you're trying to figure out where it is on the original. Not the derivative. We know the derivative equals to 0 at a critical number. We know that. That's what made it a critical number. It's making it 0. What we want to know is what is the height of this maximum on the graph. So you want to plug it into the original. All right. Now I know that's also going to equal to 0, but that's just like by accident on this one. You know what I mean? That's not always true that these are equivalent in value. So let me just write out the works to make sure we're okay. So at the critical number of x equals to 0, we have a maximum. So what you need to do is you need to find the xy coordinate. So we know that the x is 0, but we need to now find the height. So to find the height, you have to plug it into the original. So the original is f of x equals to x squared over x squared minus 9. And you're putting a 0 into this. Factored form or non-factored form, it doesn't matter. 0 over anything is 0. Okay, so the answer is this max, this relative max, is 0 over 0. And again, we got the 0 from the original function. So the highest point on this graph is 0, 0. Okay? That's nothing, nothing goes higher on this. Let me just see if I can help you with this really quick. So the idea is that this graph has a VA, just for those of you who are visual, I just sketched this really quick. Okay, this has a horizontal asymptote at 1. Okay, so this looks like the graph goes up and then up, so up, up. that needs to come in better. It's more like this. Goes up, this side goes down, and this goes like this. All right, so the graph goes up, then the graph continues to go up, but then it starts to go down. Then you hit the domain restriction, which is the VA here, and then the graph goes down. So what we found, and I just rough sketched this really fast if this helps, is right here is the relative max. That's the point on the graph, this point 0, 0, okay? So that's what you found. You found the relative max on this graph. There is no other extrema on this graph. All right, gang, that's it on this video. I hope that helped you. I'll catch you in another one. Bye-bye.